Welcome to Bari Science Lab. Today we're going to be talking about QFT, quantum field theory. Can you tell us something about quantum field theory?
No. I'm just kidding. I'm pretty sure it's an attempt to combine special relativity and quantum mechanics together, which has been an effort since both of them came into existence, because quantum mechanics essentially describes the physics of physics at a microscopic scale, while relativity, of course, describes it as at a macroscopic scale. So hypothetically combining both general theories would result in a theory of everything.
There is a misconception. People think that QFT is similar to theory of everything. Can you remove this misconception before we start the lesson?
Yes, so QFT is special relativity plus quantum mechanics, but a theory of everything would be general relativity plus quantum mechanics. So QFT is the closest we've gotten to a theory of everything, but it is not a theory of everything.
So can we call it a theory of something? A theory
speaking of theory of speaking of theory of everything, as you know, theory of everything gave us lots of hope and disappointed a lot of people. Okay, it's a theory, it's a hypothesis. It gives us only hope, nothing else. QFT also gives us hope and nothing else. Is that right?
Well, it also gives us predictions. So that's the most important thing.
Okay, is QFT only give us hope, but
in fact,
nothing else?
QFT, can get what?
In fact, QFT predicted the Higgs boson.
So QFT, we can tell that QFT is more than fantasy.
Yeah, definitely. In 2012, it was experimentally verified with the LHC.
Okay, and the Peter Higgs won the Nobel Prize.
Yeah.
But can we say that the theory of everything is still fantasy?
Yeah, so far. Yeah.
What if there is no theory of everything?
But a lot of people are working hard.
All right, so
people trying to work on the theory of everything is like people trying to work on the Riemann hypothesis. You were throwing things at a brick wall, bro.
So QFT started getting the Nobel Prize, right? And today's fantasy is tomorrow's physics. Without the fantasy, we cannot move forward. Hopefully, theory of everything will also be soon studying winning the Nobel Prize. Without further ado, let's start QFT.
Okay, great.
Guys, is this the theory of nearly everything? The TONE?
Okay,
yeah.
Let's go.
Okay, so great. So now we know a little bit about what QFT is. It's trying to combine special relativity with quantum mechanics. So what I want to show you today is a kind of brief overview of what we do in QFT. Oh, happy Merry Christmas Eve.
Oh yeah, have a very berry Christmas.
Okay. So what is the joke?
You get it? Because most people say Mary, but our last name is Barry.
That's a very funny joke.
Yeah.
Okay, back to relativity.
Do I have a strange laugh, chat? Okay. Nah, I don't laugh like that. Just to make people know that I'm not an eldritch entity. Okay, so what is special relativity in essence? Well, okay. Sorry, I forgot what I was talking about. So essentially, our theory of physics starts with Galilean reference frames. And time is just time. If you're transforming from one reference frame to another, it's guaranteed that they will have the same time at every single instance. Okay. They always experience time in the same way. And the position of this new object is equal to the position of the original object, maybe minus some offset due to its velocity. So these are the basic Galilean equations. But things...
You should draw like two reference frames here. X, T prime, X prime, and this is moving at V. But yeah, okay, keep going.
Okay. So, length is totally preserved when you're transforming between two reference frames.
Okay.
But the thing that we preserve in special relativity
is it length?
Not length.
Is it time?
Give me the black marker.
Okay.
We are not preserving length at all.
Okay.
Instead, we're preserving an unlikely thing. The speed of light, by the second postulate of relativity.
Good.
So, instead of preserving this in specific, this is very difficult to work with. So instead, we make we come up with another property, the space-time interval, which has to always be conserved no matter what reference frame you're transforming between.
Mm-hmm.
So this space-time interval is defined like this. And this is, of course, dx squared plus dy squared plus dz squared.
Okay.
So
this is a kind of length.
yes, this is the
It's
new
just,
thing that we're preserving.
It's just length, but including time.
Yeah.
So it's like a more general
in the
type of length.
in Galilean physics,
Mhm.
This is the space-time interval.
Yeah.
Well, that's technically just the space interval.
Yeah.
But
Now this is a
now,
space-time interval.
yeah, exactly.
Good.
And so this is where the entirety of special relativity, with all of its quirks, originates from. The need to conserve this property.
And what are some famous effects of special relativity?
I mean, the two most famous effects are time dilation and length contraction, which are both controlled by this factor right here, the gamma factor.
Okay.
So this factor, which is expressed as this,
1 over that.
That's the exact same thing, by the way.
No, this to the -1.
Oh crap! No, there's 1 over.
No. I mean, the gamma factor is 1 over 1 minus beta squared.
Yeah, isn't beta v over c?
Yeah, but this is just square root of that. You have to put to the -1.
Do you know?
Oh, I see. You put the 1 here. I didn't see that. Sorry. He's right. Okay, good. Keep going.
I have an M&M song that I'm going to need to show you after this. Okay, so this is essentially a measure of how much time dilates and length contracts.
Okay.
And you can see that it is related to the proportion between your velocity and the speed of light, called beta. Meaning, as beta goes up, this goes up, which means this entire thing goes down, which means the gamma factor in itself goes up.
You can just draw this v.
Yeah, it's kind of a hyperbola.
And gamma, and it looks like this. Right? And this is where v is equal to what? That's right. Okay. Okay, so is that all of special relativity?
Where am I again? Oh, yeah.
Okay,
so
good.
What is the shortcoming of the special relativity?
So special relativity does not include quantum states. This is for...
Also, it doesn't include the acceleration, right?
Actually, special relativity can incorporate acceleration using something called the Rindler metric.
Then it becomes GR.
No, GR is special relativity plus gravity. So it's a common misconception that SR doesn't include
the Riddler metric.
Rindler.
Did not know that Batman villains were getting into physics.
No, it's very simple actually. DS squared is...
No, do you not know the Riddler from Batman?
Yeah, this is the Rindler metric. And it can treat acceleration in special relativity.
But
wait, do you not know the Riddler from Batman?
Oh, maybe I do.
Riddle me this.
Okay, so that is 5 minutes of special theory of relativity. Now can you go over the quantum 5 minutes of
So
quantum?
I am not going to be included in this actually.
No. You can ask me any questions you want about quantum.
Wait. Since we're doing a video about quantum field theory, we should also be doing a video about group theory.
Okay. I consent. So let's see.
No, I was going to do it if you didn't consent.
So, okay, I'll try to summarize all of quantum mechanics in 5 minutes. Okay, ready?
Minutes, yes.
This is not going to work.
You're going to include partial derivative.
That's not part of QM, is it?
It is, but okay, let's see. I can explain the photoelectric effect.
No, everything you have to do in 5 minutes. It doesn't matter what you exclude or you don't exclude.
Okay, so quantum mechanics is all about small things. For example, atoms, electrons, protons, neutrons. It's about trying to figure out how small things behave. So to understand quantum mechanics, first you have to understand how classical mechanics behaves. So classical mechanics is Newtonian mechanics, and it can predict how big things move. So if you tell me the position and momentum of a ball at any one point in time, then I can figure out its position and momentum at any future point in time using what equation?
AM.
Using F equals ma. If you just give me the initial conditions of the ball, then I can use.
got it wrong. Sorry, it's dp/dt.
Okay, yeah, sure. Then I can use the F equals ma to predict how the ball will move in the future. So F equals.
Yeah, but that feels like it wouldn't hold up in small situations,
Yeah,
especially
but
situations like with photons that don't have any mass.
yeah, but I'm just saying F equals ma allows you to predict the future for big objects, macroscopic objects, and there's a F equals ma for quantum mechanics, and it's called Schrodinger's equation. It's actually very simple. This is Schrodinger's equation, and it.
Guys, is that an imaginary number?
Yeah, and this is a time derivative. But you can see Schrodinger's equation. I can explain to you how it works. First,
So that's the equation of a wave, and what is this?
so okay, let me label every part. So this is called psi. This is the wave function of a quantum particle, like an electron or a proton.
Yeah,
This
what is that?
is called the Hamiltonian. You can also call it the energy. It's the total energy of the particle.
Wait, bro, so
Yeah.
this is easy.
This is very easy, right? It's just saying the wave function of the particle changes depending on how much energy it has. That's it. Most people write Schrodinger's equation like, oh my god, they have to make it look as complicated as possible. This is the more expanded version of the Schrodinger equation that you will see.
Oh, because it has to expand the Hamiltonian.
Yeah, but really this is the only thing Schrodinger's equation is. It's saying that the wave function of an electron depends on how much energy it has. So what is a wave function? A wave function.
I know what a wave function is.
Okay, so what is a wave function?
I mean, okay, what I would say it is
Go
I
ahead.
mean, the wave function that you learn in oscillatory mechanics, which I just took, is this. It's just a function that describes a standing or moving wave through a wave number or a wavelength and a frequency. So how fast the wave moves. So I mean, this is what I believe a wave function is it not?
Yeah, that's a good idea. Now in quantum mechanics, things are a little bit different. See, in classical mechanics, in Newton's picture of the world, we can say if you have a ball here, then you can say, okay, this ball is right here. It has this position. Okay, let's say the ball is at this position.
Bro thinks he's Heisenberg.
And it has this much momentum. Okay, let's say, what is the units of momentum? I forgot.
Kilogram meter per second.
Oh, okay. See,
Or Newton second.
that is better than you. Okay.
No, he's not.
Okay, so this is the position.
And my student always confused, like, why kilogram meter per second is equal to Newton second, and I tell them because they are.
I don't think you're a good teacher.
No, what? Hey, have to be
No,
careful.
it's because kilogram
It's-
meter over second square, okay, over kilogram, cancel kilogram.
Yeah, that's the exact answer that you would expect the teacher to provide. Not just it is.
And I was joking.
Yeah.
Forgot that you were 12-year-old.
I take all jokes literally, including him.
Oh, wait. Well, then explain how the uncertainty principle works. Okay, I'm joking. So look,
That means you can't know the position and velocity of something.
yeah, so this is a big difference between big objects, classical objects, and very small objects like an electron. So for a classical object, you can say, okay, it's over here. You can say its position is this, and it's moving with this much momentum. But for something like an electron, you cannot tell me where the electron is and how fast it's moving at the same time. Okay, and this is because of what's called the uncertainty principle. The uncertainty principle says that you cannot tell me where the electron is and how fast it's moving at the same time. Now the question is why? Why can't you do that?
I'm guessing because if the error, either the error in the position is greater than the position, or either this and this, which means you don't reliably know the momentum.
Okay.
Or this and this, which means you don't reliably know the position.
Too complicated. You can actually explain the uncertainty principle without any math.
Yeah, you can say it in words.
No, you don't need words. You can just draw a picture. Okay? Imagine you take a picture of a bird.
Will's
Okay?
really staying true to that. If you can't explain something to
So-
a 6-year-old, you don't understand it.
So this is a bird, right?
No, that is a curved V, actually.
So imagine this is a bird. Okay? You take a picture of the bird. Okay? After you take a picture of the bird, can you tell me the position of the bird?
Well,
Yeah.
with respect to me, yeah.
Yeah, you can tell me where the position of the bird is. But can you tell me which way the bird is moving?
Not really.
No, because it could be moving this way, it can be moving that way. It's a picture, it's not a video, right? So you know what the position is, but you don't know what the momentum of the bird is. But on the other hand, you can capture, what do you call it? Exposure frame of the bird. Okay? So you can capture the bird like this.
Oh, yeah, so
Okay?
it has like a bunch of frames.
Yeah. So
Scattered
now
on
can
top.
you tell me what the
Where the bird is moving?
what the momentum of the bird is?
Yeah, it's moving
Yeah,
up.
you can tell me the momentum of the bird is here. But can you tell me what the position of the bird is?
No.
No, because you don't know if is it here, is it here, is it here? So you know the momentum, but you don't know the position anymore.
I guess then the solution to the
So-
uncertainty principle is to invent videos.
So No.
But then the problem is when electron realize that you're observing,
yeah,
I don't think
electron
this guy
changes the
knows.
behavior.
actually that's the classical proof. So if you have the wave function for an electron, let's say that this is
So video not going to help much.
Yeah,
So-
Will, trust me, man.
what is a video?
Holy crap, that looks like a infracted, diffracted interference pattern.
That's right, yeah. So when you try to capture a video of an electron, what really happens is you're sending in a photon. And the photon, by hitting the wave function, actually collapses the wave function. So what happens
Is that a Dirac delta function?
Yeah, so when you collapse a wave function, you know the position, but you no longer know the momentum. So you've broken the electron's wave-like nature. So that's why you cannot take a video of an electron to solve the uncertainty principle.
It's over, cat.
So that's the basic idea of quantum mechanics.
Okay, so we had 5 minutes of the special theory of relativity and 5 minutes of quantum.
Mhm.
Now, okay, before you go to quantum, can you just give a big idea of what you just did in like few sentences?
No, we can't.
What?
Sorry,
Let's
cat.
start with- Let's start with graph.
Oh, okay. Of quantum mechanics?
No, yeah, sure.
Okay. So quantum
No,
mechanics...
don't look at there. Look at the camera only.
Okay. So just like F equals ma describes how classical particles evolve over time, Schrodinger's equation predicts how quantum mechanical particles evolve over time. And one of the big differences between big things and small things is that you cannot exactly determine where small things are and what speed they're moving with at the same time. This is called the uncertainty principle. So that's one of the fundamental things about quantum mechanics that makes it different from classical mechanics. And
Isaac, just summarize one.
Okay, so the main idea of special relativity that makes it different from Newtonian mechanics is while Newtonian and Galilean.
What? Sorry, okay, keep it.
You will not see this.
I don't
Sorry.
see it anyway.
Okay, so what I mean is special relativity mainly differs from Newtonian physics and Galilean relativity in the sense that, time is not invariant for every single object. The thing that we conserve in Galilean physics whenever we move from one reference frame to another is length and technically time.
Mm-hmm.
But in special relativity, when you change between two reference frames, neither of those are conserved.
What is concerned?
What is conserved is the speed of light.
Why?
But, by the second postulate of relativity.
Yeah, but why did he make that postulate?
Good question.
Michelson-Morley experiment.
Oh,
Okay.
yeah, that's right. There is no such thing as a...
What year did Michelson win the Nobel Prize?
I forgot.
1901. He was the first American to win it. Okay.
Yeah, but that was the first Nobel Prize.
Yes, that's also true.
No, first Nobel Prize was 1901 or 1900.
1901.
Oh, and Michelson was the first American
first
to win the
American.
Nobel Prize.
Yeah.
He did not win 1901. He won the Nobel Prize 1903. I'm
Really?
gonna fact check
Oh no.
because this is a fact check center.
Oh no.
Fact check? More like fat check. Yeah, because I get fat checks in the mail every day, you know what I'm saying?
Wait,
Have a
do you have the
very
cap
big-
for the homework? Oh, so you had it all this time.
You have the cap for your brain. Because it's one dry.
Morley never won the Nobel Prize, right? It's Albert Michelson, right?
Yeah,
But
because Morley
but-
was the PhD student.
Yeah, that's right.
Yeah.
So
Damn, bro, postgrad's getting no credit out here. What are they even getting paid for?
Nobel
Bro,
Prize
is
in
no.
Physics actually 1907.
Oh,
Yeah, so 1901. No.
Phenomenal wait
No,
time.
but pretty close. I think he did the experiment 1903, something like that. Okay.
Bro, why do
No.
Nobel Prize committee delay Nobel Prizes for like 20 years? Are they like waiting for people to die so they don't have to be like, fine, just take it. Otherwise, people will revolt against me.
All right. So
Okay.
Q of T, you're gonna insert Q of T.
okay. Ready? Oh, okay.
Erase it.
I'm a little bit tired.
You should be
Physics
fired up
makes
after.
people tired. Never heard of it.
Yeah, because all you do is low level, simple,
God.
hot-topic, hot-headed, buffoon physics.
Oh my god. These insults. To start quantum field theory, we actually need to start with something very simple. Okay? We need to start with nothing.
Oh,
That's
oh
right,
my
nothing.
god.
So
That's brain colorized.
this is actually nothing. Okay? So quantum
Refact
field
achievements, colorized.
No. So this is what quantum field theory is about. It's actually about nothing. Okay, what do I
You
mean?
seriously expect me to believe that?
Yeah, it's about vacuum. Okay? This is the simplest physics can be, okay? The physics of a vacuum is the simplest it should be. Because there's nothing in here. There's no particles, there's no mass, there's no energy. Okay? In the vacuum, everything is zero. There's no temperature, everything is zero. Okay? In the vacuum. But quantum field theory tells us that there's no such. I think you're blocking one of the cameras. Okay.
Yeah, don't block.
So, but quantum field theory tells us that this is not possible. Okay, it tells us that this is not possible.
Wait, so if it's not possible, what can quantum field theory be about?
What quantum field theory tells us is that a vacuum, even if you take out all the air, even if you take out all the energy from the vacuum, a real vacuum will be filled with quantum field. Okay?
Oh my goodness, that's why it says quantum field theory.
That's why it's called quantum field theory.
And how it is different than gravitational field?
That's a great question. In a gravitational field,
Doesn't a gravitational field require like energy to act?
no, a gravitational field is described by a metric, g
Guff.
mu, and a gravitational field is created by a mass. So
And
when
how it is different than electric field?
I'll explain. But first, let's see how it's different from a gravitational field. Let's call this quantum field phi.
Do you need energy
Okay,
for this?
wait.
quantum
Okay,
field?
I'll answer it. But first, Dad's question was how are these two things different? Okay, so the gravitational field, if you make a small disturbance in the gravitational field, what is a small disturbance? A small disturbance means you can move the mass from here to here, for example. If you make a disturbance in the gravitational field, what happens?
It causes a gravitational wave.
Yes,
Or a
that's right.
fluctuation in the quantity of gravity.
So if you move the sun, for example, then the gravitational field of the sun will move with the sun, and it will move at the speed of.
The speed of
Light.
light. It
Speed
takes
of
8
light.
minutes.
That's right. That's right.
Wait, so does the speed of gravity in water act slower?
I don't know. Let's.
Holy crap, this guy's so dumb!
Okay. So disturbances in the gravitational field, a disturbance in the gravitational field creates a gravitational wave.
And the speed of gravitational wave is the speed of light.
It's the speed of light. Yes. Travels at c. What about an electric field? Let's look at an electric field. So here is a electron. It creates an electric field like this. Now what happens if the electron moves from here to here? What do you think happens? Can you draw the new electric field lines at this location?
Yeah, I mean, before. Now, the electric field lines look like this, which caused us.
But
Wait, crap. Am I dumb?
no,
Shouldn't
it's
it
okay.
be going inward?
Oh yes.
Electron inward and proton
Sorry.
outward.
Sorry,
Electron proton. You did actually proton.
yes.
Well, clearly it
That's
says
right.
E minus.
Can you
Okay,
erase?
E
Can
minus.
you erase it? It's
Yeah,
so
let's-
confusing. Yeah. So,
Let me draw it nicely. This is the electron.
When you write E, don't write E, just minus or just
Okay.
electron. Yeah.
This is what we call the Regent physics diagram.
So this is the electric field of an electron. When the electron moves over here, then the electric field moves from where it originally was to here. But the electric field lines over here don't know the electron moved. So they're actually going to stay here. And only the electric field lines closer to the electron will move first.
Oh, it's kind of like at the
So
speed of light.
it actually looks like a spider web. This is what the new electric field looks like. It doesn't look like just straight lines. So when the electron moves, the electric field lines don't change immediately. How fast do they change?
At the speed of light.
At the speed of light. Because when the electron moves, it actually releases a photon. And that photon is an electromagnetic wave. It's light.
This is also speed of light.
Because it is light. It is light. So a disturbance in the electromagnetic
use this
field.
opportunity to tell us the differences between electron and light itself.
What?
So
I mean, light is
an
composed
electron-
of photons. Photons are not electrons.
Yeah.
an
but
electron
the
has a
moving
mass.
Moving electron is the light. Yeah.
That's right. So an electron has a mass. Photons
Don't have mass.
Photons don't have any mass. That's the first and most biggest difference. That means
Most biggest? Most
That's right.
biggest?
So
Most biggest? Chad,
If
is
you
he
have-
really a native English speaker?
if you have an electron, then the energy of the electron is not just the rest mass. It's also the momentum of the electron. So this is the energy of an electron that's moving. But the energy of a photon is just hf.
Energy of yes.
So this is the second difference. The energy of a photon depends on its color. A red photon, is it more or less energetic than a blue photon?
I'm guessing it's
Blue is more energetic.
wait, no,
That's
bro. I was about to remember it using ultraviolet.
No
and-
memorization required. You just plug in. Okay. So that's
Oh,
another
you plug in
difference
what? Plug in
between-
what?
Between an electron and
Plug in what? Plug in what?
Oh, okay.
Plug in what? You little...
You plug in the frequency.
Wait, so you have to memorize the frequency.
No.
You lied to me.
Okay.
You lied.
Another way you can see the difference between an electron and a proton and a photon is you can graph the energy versus the momentum. So
That
for
is not momentum.
for an electron, this is the energy graph. For a photon, this is the energy graph. E is equal to hf. So you can see that the energy of the photon depends only on its momentum.
What
But
do y'all know about the thing?
Yeah, this is the energy of the electron.
Yeah, which means when this is out of the picture, it's just linear.
That's right. So this is the difference between an electron and a photon. So notice
Okay, you
Yeah.
show us the difference. What is the similarity?
between an electron and photon,
Because one moving electron creates the light.
why does a moving electron create light? That's a good question. The answer is conservation of energy.
Or the answer is you don't know.
No, it's conservation of energy.
Okay.
Because let's consider the hydrogen atom. This is minus 13.6. And let's say this is what? 2.8?
This is the next one.
Yeah,
Minus
13.6 over
13.6
4.
divided by 4.
What is, let's say just
Negative 3.4.
3.4. That's right. Okay, good. So when an electron jumps from the first excited state to the ground state, it lost energy,
It
right?
does.
Somehow it has to express that loss of energy.
Okay.
How can it express that loss of energy? You can ask the question, what are the internal degrees of freedom of the electron? The electron has a mass, it has a spin, and it has a charge. Can the mass of the electron change?
No.
No.
Conservation of mass.
Can the
And
charge?
conservation of
Can the charge of the electron change?
No, but
No.
the spin can.
Can the spin of the electron change?
Yeah.
Only if it's placed in an external magnetic field.
Oh, so the electromagnetic field created by this move
So so there are two ways you can think about it.
So
the-
why electrons are excited and why they jump down?
Oh, that's a good question. The answer to that question is actually what bothered
Both.
Heisenberg and Bohr for a long time,
Mm.
because there is actually no cause and effect. There is no cause that makes the electron excite, and there is no effect that makes it jump down. The weird thing is it happens without a cause and effect.
So why they tell us that when they gain energy, right?
Yeah.
They jump up, and when they
Because it
jump
was-
down, they lose energy.
Because it would confuse Regent students too much to just say it doesn't happen with a cause. There's no cause.
No, it is true when the electron jumps down, right?
It loses energy. Yeah,
It has
of course.
to
It loses
release a
energy.
photon,
Okay.
and
When it jump up,
when it jumps up, oh, okay, then it cannot jump up without gaining the energy. That's true. But when does the electron decide to jump down, and when does it decide to jump up?
It
That
doesn't
happens without
happen-
cause and effect.
okay.
Yeah, it doesn't happen
But there
immediately
are
after the
requirements
kid.
to jump down or jump up.
There were
There
requirements.
is, yeah.
And
There are,
if
yeah.
they don't gain 3.4,
That's
then
right.
they cannot jump up.
Yeah,
If they don't
But
gain,
they don't go up or go down instantly after getting hit by light.
yeah, if they don't
Oh.
gain this energy, then they will never jump up. But
Even if they are excited, they don't have to jump down.
Yeah.
Yeah.
They have the
That's right.
qualifications
So-
to jump down, but maybe
so-
they don't have the desire.
for example, let me give an example. Okay,
So
here.
number.
See, all of these electrons are in the first excited state, right? Okay, let's say t equals 0, so time is 0 at the beginning. So you wait for 1 second, and you see this electron has jumped down and it released a photon. How do you know this one has come to the ground state? Because you can see with your eyes that the photon has been released. But after 1 second, you see that this one, you don't see any light from these two still. You see that they are still in the excited state. So you wait 2 seconds. Still, they're both in the excited state. You wait 3 seconds. And then you see that the third
So
one,
they have what it takes to jump down, but they don't have to.
they don't have
They
to,
don't
yeah.
have the desire.
So it's completely random as far as we know why they jump down. Or another way to put it is, if you can find out what causes them to jump down, then you will win a Nobel Prize tomorrow.
Maybe it's dark matter.
Yeah.
Okay, all right.
But what if the Nobel Prize isn't
Okay,
getting
so
for
no.
tomorrow?
Okay, so you were discussing. Don't forget where you started from. You were
Mhm.
discussing the quantum field, and I asked you
Yeah.
what is the gravitational field, and I asked you what is the electric field.
Mhm.
Would it be relevant to discuss the magnetic field or no?
That's kind of a magnetic field is just an electric field that is moving. So if
A
you
dynamic electric field is the magnetic field.
That's right. So if you have a magnetic field, let me see. Let's draw it here. For example, if you have this electron, and the electron starts moving, as soon as the electron starts moving, it creates a magnetic field, because a magnetic field is just a changing electric
Yeah,
field.
that's Orsted.
That's
discovered,
right.
A moving.
more like the first law of math.
That's right. So Faraday's law tells us that if the electric field is changing, it immediately creates a magnetic field. So
Okay, and two other forces: nuclear force, strong nuclear force, weak nuclear force.
Isn't
They
that
do
chem-
not create any field.
actually, I don't know anything about them. So
Okay. That's
See, chemistry is its own
I
science.
cannot
This,
comment on that.
this guy is a physicist and he doesn't know chemistry, which means chemistry is not part of physics.
all right. Now let's
Okay.
go back. Good.
So going back to quantum fields. So we talked about gravitational fields. What does a disturbance in a gravitational field create?
A gravitational wave or
Okay.
a fluctuation in the amount of gravity that travels
Yeah.
at the speed of light.
For example, if you remove the sun from the solar system, how long will it take for the Earth to know?
Yeah,
8
it's
minutes.
like a lag.
It's like a lag, yeah. And if you have a disturbance in the electric
it's
field,
like a lag. If you pick up the phone, if you dial,
Mhm.
and if someone in India pick up the phone, how long does it take? What is the lag?
Like 1 second or so.
Actually, I don't know.
No, like 1 second. I mean, telephone lines don't travel at the speed of light.
And if you have a disturbance in the electric field, what does it create?
If you have a disturbance in the electric field, it creates a magnetic field or electromagnetic wave, right?
A changing electric field creates a magnetic field, but a disturbance in the electromagnetic field creates light, right?
Well, yeah, because the electric field creates a magnetic field, and then that magnetic field creates an electric
Yeah.
field, and it starts a chain reaction that creates light.
Yeah. Okay.
Well, chain reaction is what creates light.
Yeah, light is the electromagnetic field.
Field, yes.
Yeah.
So you did not draw the the
The
graph, but it's
picture.
okay.
Yeah.
Yeah, it's fine.
But this is the picture of light. This is the electric field.
And where is the magnetic field?
Oh my goodness, we
And-
got a real colorized picture of
Oh,
light.
can I get the red? Let me get the red. Okay.
Can you draw the what is perpendicular?
Yes.
Is this perpendicular? What do you call that?
Oh,
This is
transverse wave.
No, this is
Oh.
electric.
This one.
No, this is magnetic, and then what is electric? Okay.
This is the electric field. So this is what light is.
Holy moly!
So, right,
We
we-
used light to take a
Yeah.
picture of light.
So this is light, and it travels at 3 times 10 to the 8. Okay. So disturbance in a gravitational field creates a gravitational wave. Disturbance. This is what LIGO detected in 2015.
We won the Nobel Prize. Yeah.
Yeah. Yeah.
Me?
Yes.
Which
Okay.
means human
All physics.
human species.
Yeah. So don't we win the Nobel Prize every time?
I'm proud of Joe. I'm proud of Jack. I'm proud of all those.
I don't think anyone
Anthony.
named Joe.
All those people who win the Nobel Prize on behalf of me.
No. This guy can actually see the future because the first dog wins the Nobel Prize in 2178. Once all
Why
animals
you
are
have,
weak.
why I have to be so jealous? Not be proud of someone who win the Nobel Prize.
The Nobel Prize was made for humans by humans. So if a human wins the Nobel Prize, it's not anything out of the ordinary.
All right.
Okay. So
I'm sure if I win the Nobel Prize, some people will be proud of me.
Well, yeah, most
Yeah,
people
of
would be
course.
proud of you, but not because
we would
you're
be
a
the
human.
proudest.
You would be the proudest.
Okay. So
I would be questioning if, like, the Nobel Prize committee was sniffing drugs, they were replaced or something.
they were taking hostages. Right? Okay.
Because there's no way in their right mind they
I
decide
thought
to
you
give
saved
it.
this one for Christmas Day.
No, I got even worse stuff packed up.
Okay.
And I know you might be asking, how can it get worse? Just look at your own life.
Okay.
Go ahead.
So you get the point, right? Disturbances create things. So what does a disturbance in the quantum field create? What do you
I'm
think?
guessing quantum wave, quantum chakra.
No, it's not a quantum wave.
Is it a quantum chakra?
No.
Quantum time travel?
No.
Quantum meditation?
Okay, a disturbance in the quantum field creates objects.
Really?
So this is the amazing thing about quantum field theory.
Disturbance in quantum
In the quantum field
creates.
creates
Quantum.
objects.
I thought, is it a Higgs field?
That's one example. So this could be a Higgs field, and a disturbance in the Higgs field creates a Higgs boson. So it creates an object.
Yes.
It creates mass. It can create things out of nowhere.
Okay.
That's what a quantum field is. It can create. So it's like almost like God. It can create particles. Okay.
Quantum field theory is God theory? Confirmed?
No.
We proved the...
Listen. What I'm
Oh,
saying
this is just
that-
like that rant Dad went on saying F equals MA is proof that
Okay,
I
but
love
what I'm saying is
You still debating, baby? You still debating after all the convincing? You know, if F equal ma is not because why God loves us, it would not be F equal ma. It would be F equal M N Q R P T E J I Q M psi L P N 2 square 9 pi Q square M T Y square.
Yeah, just look at the Christoffel symbols, for example.
oh that's
No,
true.
Christopher's symbol is not as fundamental as F equal ma.
Yes, it is.
F equal ma is bigger than universe because it can create.
Stop. This guy did not know what he's talking about. Christoffel symbols aren't fundamental. Shut up! It's been 15 years since you took a legitimate physics class. And you've never taught a legitimate physics class.
Oh, me?
No, him.
Oh. I was gonna debate. Okay. So that's what happens. A disturbance in
So
gravitational
do not
field.
disrespect F equal M.
Is it like a person? Can I like roast it? F equals MA only has 3 letters? Bruh, so little.
Okay. So disturbance in the quantum field creates particles. Okay. Now I'm just saying words. Is there an equation to back this up?
No!
Yes, there is. So let's write down the equation. So, but do you have any
creating
questions?
particles out of nowhere?
Yeah.
That smells like it would violate the conservation of energy.
Oh, well,
Right?
that's why we also, at the same time you create a particle.
You create an anti-particle?
That's right. You can create an antiparticle.
And by accident, more antiparticle than the particles, and the universe is a result of
More particles than antiparticles.
more particles. Okay.
This is called the baryogenesis problem.
Do we know where the antiparticles went yet?
I don't know. No.
Maybe the antiparticles are what make up dark matter.
Dark matter is not science yet.
Well, I mean,
What?
it is. Does he know what he's talking about?
No, dark
We
matter
know it has to exist. Unless our current model of physics is just
My
wrong.
standard is very high. I don't consider everything physics.
My standards are very high. I don't consider everything physics. The guy who does algebra-based physics 1 for high schoolers. Maybe middle schoolers, but for bad high schoolers.
And also, I don't consider inflationary theory as physics.
What?
I don't consider string theory as physics. My standard is bar is very high.
He doesn't even teach AP Physics 1 yet. What are we talking about? You should rise up the physics teacher ranks before you say something like this. Like, at least teach like AP Physics 2 calculus based or something.
That's not relevant here, but I'm saying that
You have no credentials for, like judging whether something is real physics when you do something that's barely even physics.
Oh my god.
You know?
Okay.
What I'm feeling?
So this is a quantum field. To describe how a quantum field behaves, you cannot use F equals ma, because this is something quantum, and you cannot use Schrodinger's equation because this is something relativistic. The fields can move at relativistic speeds, and Schrodinger's equation
is the quantum version of F equal ma.
That's right.
And
but,
so they must have
but
a
it's
child.
not the relativistic version.
Yeah.
So to fix that, you need
So when I said F equal ma is everything, I do not exaggerate.
Yeah, that's
that.
right. So, can you write down the total energy of a spring?
This guy always be producing Jabberwocky from out of his mouth.
Okay.
You know that Jabberwocky was.
But no gravity. No gravity.
Okay. So then it
just purely Hooke's law.
Yeah.
See, Hooke is better than
Okay,
Newton.
good.
Hooke is better than Newton?
I'm about to be killed. See, that's why my name should actually be changed to Suborno Robert Bari. Because Robert Hooke is the best physicist out there.
Okay.
So getting worse than Mahoney brothers.
So for a quantum field, the total Lagrangian looks almost the same as for a spring.
Holy moly, does that mean springs are made of dark matter?
So can you guess what it'll be?
No.
Just replace x with phi and write the same thing.
Oh, interesting.
Yeah.
Wait, we're squaring the wave equation?
Yeah, go ahead.
You're a weirdo, man.
No, x with phi. It doesn't really matter.
Oh, you mean psi?
No, this is phi, yeah.
Not psi, okay.
No, not psi.
Die.
And replace k with the mass.
K
with mass squared.
Wait, that looked like a rotational kinetic energy.
And so this is the Lagrangian for a quantum field. So this is very powerful. So the way you usually write it is like this. And if you plug this into the Euler-Lagrange equation, then guess what you get?
What?
You get the Schrodinger equation, but in the relativistic version.
Bruh, what?
So you get this.
We're not actually gonna solve it today, are we?
No, but this is the equation you get.
Holy
And
moly!
if mass is 0, then you should recognize this equation because you learned it in physics 3. What is this equation if mass is 0? What does it mean for mass to be 0? There's only one. You don't have to solve it. There's only one thing in the universe that has a mass of 0.
Light.
Light. So what should this reduce to if mass is 0? You should be able to write it without calculating.
Well, I mean this, no?
No, not quite. Almost. Remember, this is a 4 derivative.
4 derivative?
Yeah. So if mass is 0, this is 0.
Light doesn't have mass, but it has momentum.
Has a momentum. Yeah.
So light has a relativistic mass.
I don't think he knows how to.
Huh?
Wait, what?
What do you call it? What type of mass you call it? The light mass.
Rest.
There is a-
Light does not have rest mass or.
There is a
Relativistic
word
mass.
for it.
There's no word for it.
No.
This is the rest mass.
Yeah, rest mass never changes. Yeah.
Yeah.
But the light.
It does not have
It
relativistic.
doesn't have any mass.
Okay. So So it does have momentum.
It has momentum, and so the energy is.
It has a concept analogous to momentum emerging from.
Yeah.
Because of frequency.
Mhm.
Okay.
So momentum of a real life object depends on how much mass it has. But light has no mass, so you might.
Why are you patting me when you talk about mass? Are you telling me I'm massive?
No, but light has no
Do you
mass.
know what else is massive?
Okay, no. Okay, so this is the equation if mass is 0. So now this is a 4 vector. So remember, don't forget your phi. So what is this equation? What is this?
Well, the equation we learned in was just this. Oh, okay, never mind. This is literally just a wave equation
That's right. Wave equation with what speed?
with the speed of light.
Yeah. So
Holy
that
shit.
means the quantum field is like, if the quantum field has no mass, then it can describe the propagation of photons. But in general, a quantum field has this mass term.
Wait,
So
actually,
you have this.
any phi could solve this. No?
Yeah.
Well-
Can you guess a solution?
Well, I mean, any solution. Would take
Exactly.
this form.
Exactly.
But I mean, couldn't this frequency be anything?
What?
Couldn't this frequency be anything?
No. This. If you plug this in over here, guess what you get?
What? The speed of light?
No. You get something you know. If you plug your guess back into over here, what do you get? You get the most famous equation in all of physics. E equals mc squared comes from here. So if you plug in this guess that you just wrote this down, right, as a guess.
Yeah.
If you plug it back into this equation for the quantum field, you get E equals mc squared.
I think this is the first time Dad's seeing the derivation of E equals mc squared.
Yeah.
And this is the first time I'm seeing it in such like
No,
a
this is
beautiful
not
manner.
a traditional derivation of E equal mc squared.
Well, there are many ways to derive it. There's a second way to derive it that I know, starting from.
Yeah. Wait, this is actually.
This is really amazing way of
Yeah.
deriving. Did you just derive the E equal mc squared?
Yeah, I can show you. I didn't show the
Yeah,
step.
This is
Why don't
super
you show
cool,
us?
bro.
Why don't you show?
Wait,
Okay, so here are the steps.
really?
Yeah,
So
this is like an open conversation.
Yeah.
Physics shows the direction we take. Tomorrow is Christmas. Yeah, that's true.
okay. Although I am
Oh.
hungry, so after the derivation.
That's right.
Okay.
Okay,
So
5
look.
more minutes.
Look.
I give both of you 5 minutes to finish it.
Okay. So
After 5 minutes, you're gonna have to pause.
yeah.
Pause? I thought you mean finish, right?
Okay.
Right?
I'm gonna
Yeah,
derive.
sure,
I'm
finish.
gonna derive E equals mc squared. Ready?
Yeah.
Okay. So, but I'm gonna ask you to guide me through it.
Wait, okay, so
Okay. In fact, you do it.
so
Okay.
do we just plug in the guess?
No. First thing I want you to do. You can't just plug in the guess.
Before you prove E equal mc squared,
Yeah.
derive E equal mc squared, you have to tell people what just you wrote.
Okay. So can you explain?
I mean, this is the Lagrangian for quantum field, is it not?
Yeah, so this, imagine you have a box with nothing. Even nothing has something, according to quantum field theory. This is a box of nothing. And even if you take out all the air from the box, even if you take out all the particles from the box, this
Anything
nothing,
that is physically in
And
the
also-
universe is
Also,
permeated by
let's
some
use this
quantum field.
opportunity to add the fact of the matter that the quantum field theory came after Einstein uh, derived E equal mc squared.
yeah,
So E equal mc squared derivation happened before 1905, and
yeah.
quantum field theory came after 1925.
Wait, I'm about to
Oh.
say something incredibly.
Okay. Let's go.
Did I say
Okay,
it?
no.
Okay.
Okay. So, you cannot just plug in. Oh,
Why?
so first let me explain what this is. This is the equation for a quantum field inside a vacuum, inside a box.
Yeah, and the quantum field equation in specific is this.
So this is what this is.
5 variables.
So now can you write down the Euler-Lagrange equation?
Yeah. So the Euler-Lagrange equation is actually I forget.
That's okay. Just write down what you remember.
Something like this.
That's exactly right. Now upgrade it to QFT. Okay. So I'll show you how to upgrade it here.
What do you mean upgraded?
So you see how this is a time derivative?
Yeah.
We're gonna take all derivatives at the same time.
Holy moly!
And you see how this is a time derivative?
That is not a time derivative.
You wrote dot.
Oh, that's a derivative with respect to time of the space derivative.
No, it's a time derivative.
Yeah, it's the derivative with respect to the time
Yeah.
derivative of space.
That's right. So you see how this is a time derivative?
Yes.
Okay, we're gonna take all derivatives at the same time.
Bro, how is this
Okay.
possible?
So this is what makes the theory relativistic. Okay. So now I'm going to write the general form of the Euler-Lagrange equation, which is this. Okay, good.
You literally just
This
moved
is
it to the other
yeah,
side.
it's just the same thing, right? Same thing. Okay. Now I'm gonna get F equals ma for the quantum field. So I'm gonna ask you to take the derivatives. Go ahead. First calculate this one from this.
Okay, so that's gonna be pretty difficult though, right? So this
No,
is equal to.
just use power rule, product rule. If you still
I
remember.
mean,
that.
that's a. You want to throw hands?
No. Go ahead.
I'm gonna go right for the big red spot. Okay. So we have. Let's see.
So you
5
have to be
squared.
careful. This
Oh
is
wait,
with
that's a
this-
constant.
That's just
so,
a constant. That doesn't show up. Okay, good.
Okay.
Now, can you take this derivative, apply it here? Okay, good. Now, can you take this derivative?
I mean, isn't that just minus 2m?
Don't forget, there's a 1/2.
Yeah.
And don't forget, this is m squared.
Um.
This is m squared, right?
Oh.
So,
Oh.
okay, good. So, can you write down
I thought we were taking the derivative with respect to m, bro.
Yeah.
I'm dumb.
Now, can you write down the full solution you just got?
Okay, so now we just have. Because that kind of looks like.
Nope, that's wrong. You have to be careful with your signs. Okay, now can you put everything to one side and factor out 5?
Factor out?
Factor out 5. Yeah.
What the? Wait, so essentially, we have this, and you're just telling me to freaking.
Yep, just factor it out. Imagine there's nothing wrong with it. Just factor it out. Yeah, don't worry, the mathematicians will approve this. Just factor
No, the
out
mathematicians do not.
Factor out 5.
I spoke with the mathematicians committee about this exact same thing, and they don't approve of it. What are you telling me to do? What is this?
Okay, now step aside.
What are you doing?
Okay, so this is F equals ma for a quantum field.
That is not F.
This is F equals ma for a quantum field. It's so important. It has a name. It's called the Klein-Gordon equation.
Well, most equations in math and physics have a name.
Okay. Now from this one we can get equals mc squared.
Even the Bari equation has a name, and it's pretty.
Yeah.
Very important.
By plugging in your guess. Can you write down your guess again?
Okay.
Write down your
So
guess.
I mean, my guess was e
Let
to
me
the.
let me erase this so you can write it nicely. You'll see equals MC squared comes out of this.
I mean, my
Very
guess was e to the I kx minus omega t. So
equals. What is this a guess for?
it's for phi.
For phi.
So if I plug that in,
Oh, can you write phi?
So-
Equals, no, because I just wanted to be clear.
okay.
Write phi equals.
So
okay.
if we're taking this in every derivative, don't in every coordinate, don't we have two equations?
And can you write a dot product here so that it's general? Okay. Good.
Okay.
Now go ahead, take the derivative.
So we have, I'm guessing, two equations. One for the x direction, which gives me what? So I kx.
By the
means-
way, I'll let you know the 4 vector for momentum is EP comma K.
why are you
don't-
using k for this and for the wave number, bruh?
Because this is the wave vector inside. But you can go ahead.
Okay,
Go
minus
ahead.
k squared e to the I kx minus omega t
Okay.
plus m squared e to the I kx minus omega t. Now, obviously, these.
Wait, you forgot one more derivative, the time derivative. Remember, this is a 4 derivative.
Isn't that in the other?
No, it's not a separate equation. It's a 4 derivative, so it's in the same equation. So you have to do plus. Okay. Plus.
Oh, that's interesting. Okay,
Okay.
that's one. That's definitely one of the ways of all time of going about it.
Yeah.
So then minus omega squared
Okay.
t plus m squared.
Okay. No, you already wrote m squared. You already wrote
Oh.
m squared.
Oh yeah, crud.
Okay.
Okay, so that is equal to 0, and can I just erase all of these exponentials?
Yeah,
since they can
just
never be
divide
equal
by
to
them,
0?
And remember, in the 4 vector for wave, for the wave, the 4 vector for momentum, energy is equal to the angular frequency.
Energy is equal to the.
So you can replace W by E.
Okay, so minus k squared plus m squared minus e squared.
Yeah. So solve for E. I think you messed up your sign. This should be plus. It's plus for a reason that you probably.
Oh crap! Oh yeah.
Because you're using the Minkowski method.
No, I did a very big stupid. You know why? Because.
No, you didn't make a
No,
mistake.
this was supposed to be. I made a sign issue, and of course, if you flip the signs.
Okay, so can you solve
okay.
for the energy?
I did a big sign oopsie because I forgot this existed.
Okay.
So that means that we have.
Remember, you can, yeah.
Energy squared is equal to k squared plus m squared.
Okay, solve for the energy.
Okay.
Okay, and now you're almost there. Do you see how to turn this into equals mc squared? Think about how this is very close to
I
equals
do
MC
remember that E equals mc squared takes
Okay.
some a form like this.
Write it in the squared form.
Okay.
No. Write it in mc squared plus, right?
Yeah.
Okay. So
Is k equal to pc or
why would k equal pc?
what is k? What is
K is the wave vector.
Okay, and
So do you have you
Omega. No, I'm sorry. Yeah, omega t.
what is broken down?
not quite. What is the equation for de Broglie wavelength? Do you know?
I forgot. Oh
Yes,
wait.
not HF.
Very close.
Yeah.
Lambda f is equal to v.
This is the de Broglie wavelength.
Oh yeah, crap.
Right?
P is equal to h over lambda.
And
Okay.
remember, k, the wave vector, is 2 pi over lambda, right?
Oh,
Can you find a way?
That's right. So yeah.
Can you
Wait.
relate p and k?
Wait, so that means that
Yeah.
lambda is equal to h over p, which means that if I
Okay.
plug it into this equation,
Okay.
it should give me 2 pi times p over h.
Okay. And you're almost there. Now,
Oh, is 2 pi over h c?
no, 2 pi over h is not c. Here. So p is h over lambda, right?
Yeah.
And k is 2 pi over lambda,
Yeah.
right? So if I just write lambda is 2 pi over k, then I can plug this in over here, and I can get P is equal to, I think you're blocking, move. So P is H
Over 2
k
pi
over 2 pi. But H over 2 pi is H bar. So that means P is H bar k,
Yeah.
right? So in quantum field theory, we set H bar to 1.
And you also set the speed of light to 1?
Yeah, but we'll reintroduce them. So what can you replace k by?
Just P.
Just P. And what did you do? How did you do that?
I mean, just combining these two. Well, then
That's
you can
right.
also set this to 1 as well.
Yeah.
Yeah, I derived
So
it.
we used the de Broglie wavelength to come up with this. And now you can put C back to get the full Einstein equation. So you can put the C squared back and the PC back. And then you
Does
get,
that look familiar?
and then when the momentum is 0, then you get just the rest energy.
So
Which is what?
You gotta make
That's
it
it.
clearable
Yeah.
for that size.
Okay, yeah, that's it. That's the derivation of E equals MC squared.
All right, summarize. Go over there. Okay, so how the nothing, from nothing, you first derive F equal ma and then derive equal MC squared. Ref, you travel from nothing to F equal ma, and Isaac travel from F equal ma to E equal MC squared. First
Okay.
go Ref.
So we started with the
Don't have to show. Yeah.
Okay. So we started with the equation for a spring, and then by plugging it into the Euler-Lagrange equation, we got F equals ma for a quantum field.
Isaac.
I'm blue, da booty, da booty. Oh wait, we were supposed to learn something. Okay, I'm just kidding. So I mean, we plugged it into the Euler-Lagrange equation derived from the principle of least action, and then we plugged in a test guess, e to the I times kx minus omega t, which is basically the form that every wave equation takes the form of. So I mean, we have this equation. We plug in our guess for phi, and we just kept simplifying. Then we use the equation for de Broglie wavelength in order to simplify. I mean, we already have this equation right here, which is literally the wave equation. But we can plug our guess into this to get even more simplification in the form of this equation right over here. So that gets us to k squared plus m squared minus omega squared is 0. And because of the energy of this photon is equal to omega, which means that we can just plug omega in as.
Do you know why it's equal to omega?
No.
Because look, what is omega equal to?
Omega's frequency, so 2 pi over
2 pi f.
Yeah, 2 pi f.
So pi f is equal to.
And E is HF.
Oh,
right?
so 2 pi over, okay.
So if you plug this in, then this is
That's why I said omega.
H bar omega.
So what happened is like mean value theorem. From A to B, you must cross the 0. From nothing,
Intermediate
Yeah.
value theorem.
intermediate value theorem.
Do you even know what the mean value theorem says? It says for any continuous and differentiable curve, it says
No. Don't.
it says if you have A and B and a continuously differentiable curve between them, then then at some point the tangent line is parallel to the line between A and B.
I meant to say intermediate.
That's actually the method that I use for a Putnam problem.
Okay, no, let's not change the subject. I was going to make an analogy with intermediate value theorem. From A to B, you must cross 0. Here, from nothing to equal MC squared, you must go through F equal M.
What is that talking about?
Yeah, well, you have to
What
start
is the connection
from,
between F equal M and equal MC
They
squared?
both contain a M right next to the equal sign.
Okay, go ahead.
That's true. F equals ma.
Wait, no. It's
No,
actually. Wait, no. It's actually super easy, Chad.
What?
Look. It's super easy. All you have to do is do that.
Yeah, sure. Okay, go.
Actually, the connection between F equals ma and equals mc squared is very clear, because F equals ma is the force on a big object, and if you exert a force on a big object, you give it some kinetic energy, right? 1/2 mv
Yeah, and you're
squared.
gonna say energy has something to do with equals
No.
mc squared.
In the limit that v approaches 0, you can show that E equals mc squared approaches 1/2 mv squared. In fact, I can show that now.
No, please.
You can see that very clearly. So that's the connection.
Say it again.
Maybe if I show it, it'll
Yeah.
make more sense. So here,
Erase it.
this.
Isaac, one more minute,
So-
and then you have to.
So what I'm saying is that Einstein wrote down this equation, right, for the energy of a relativistic particle.
That's equivalence sphere.
That's right. In the limit that the velocity is much less than c, this actually just reduces to 1/2 mv squared, which is the kinetic energy of a macroscopic particle, and you can show that very easily. So you want me to tell you? Just factor out the mc squared. Factor out the mc squared. Whole square.
Bro,
Give him more space. Erase
Yeah.
some of the thing.
I'm kind of dazed right now.
Yeah,
I
me
don't know
too.
if you can tell.
But let's do this one and see how you get kinetic energy. No, you factored it out, so something has to be outside.
Yeah, I know.
Okay, let me see if you factored it out right. That was too fast even for me. Let's see.
Bruh,
So he
I
factored
think
out
you're
mc
really
squared.
slow.
So you get 1 plus pc over mc squared. Okay, that's how you got that?
Yes.
Let me do it because
Bro, what?
let me see if I get the same thing.
This guy has
So-
trust issues, and this guy has learning issues.
If you factor this out, then you get pc over mc squared. Oh, good. Okay, so you did it correctly. Okay, good.
Art thou slow?
So, okay, now do you know how to do Taylor approximation on a square root?
I am so dazed.
Okay, then I'll do it.
I could, but I'm not going to.
So this is mc squared times square root of this. So Taylor expansion of this gives you 1 plus 1/2 of p squared over mc whole squared. Okay? Now you plug.
That's the Taylor approximation in first order.
This is the first order Taylor. So plus 1/2.
order.
What?
First order.
Yeah, this is the first order.
Yeah, I just said
Okay.
that.
So mc squared p squared over m
See, guys, I'm recording, so don't forget that.
Yeah. Okay. So
1
this,
over m.
This is a constant term that won't affect the equation of motion. We're gonna set it to 0. Okay. M.
Oh, so that is
M
half m.
cancels out. Okay? Why don't you do it? I don't wanna fake it. So go ahead. Can you do it slowly so people can see? It's real.
Seeing my.
That's how 1/2 mv squared comes out of E equals mc squared.